Hello, everyone. Thanks to the organizers for inviting me to this workshop, and thank you all for listening. So, the title of this workshop is Learning from Limited Data. And in that vein, I'll be talking about one particular form of data that's extremely challenging to obtain, particularly for complex tasks, which is labels, right? So, we'll be talking about alternative forms of labels, particularly in the form of preferences, and how we can learn jointly from preferences and labels. So let me start by motivating the use of preferences. This has come up quite a bit in literature. And the reason is that preference feedback can be easier to obtain and it can be more accurate. So, as an example, you've probably all been to an optometrist at some point, and if they want to evaluate, how good your vision is, or evaluate the fit of a particular like glasses or lenses, then they always ask you to compare, right? They'll show you one lens and then another lens and say, is this better or is that better, right? They never ask you to rate a particular lens that they might be using. And the reason is because ratings are much harder, right? Whereas doing comparisons between different lenses is a much easier task on which we tend to be more accurate. So this is an optimization task where the optometrist is trying to evaluate the fit, right, of the lens to your eyes. But similar things come up in other domains. For example, reinforcement learning is another paradigm where it's easier to specify which trajectory taken by an agent is preferred over another one, whereas trying to come up with specific reward metrics, which is the supervision in this case, may be very hard depending on the task. For example, if you task a cleaning robot to clean, right, then you have to specify a reward metric for it. And if it's the amount of dirt collected, or if it's a reward based off if the robot is seeing any mess, then there are many ways to get around it, right? But it's easy for to elicit expert judgment in terms of which is a preferred trajectory, right? Which is a preferred mode of operation of the agent. So that's again another scenario where preference feedback is much easier than trying to specify a handcrafted reward metric that will reflect a complex goal that the agent is actually trying to accomplish, right? Other scenarios can include supervised problems, more classical, like regression, where if you're given a person's face image and you have to estimate their age, then coming up with that age estimate is much harder than looking at two images and saying who looks older, right? We tend to be more accurate on doing that than trying to estimate the actual ages. Another problem that I've encountered in my work is classification. So, in particular, here the application was deciding which parts are 3D printable. So, the Army has and the Navy, I think a lot of them face this issue where they have a lot of list of parts that can potentially be 3D printed. But to actually figure out if the part is 3D printable, you have to go through an entire design process to figure out how to implement the 3D printing of the part and then actually try to print it, and that's a very time consuming and expensive process. So instead, it's mostly expert decisions that are sought on, can they figure out between pairs of parts which one is more printable, or come up with a ranking of all the parts. So that's again a type of preference feedback that tends to be easier than trying to have them rate each particular part on its 3D printability. So, having seen some examples, let me define the setup a little bit more formally. We are thinking about two types of queries. Either the algorithm can choose a particular X and get to observe its label Y, which depends on some underlying labeling function, right, at X, or it can choose to do a comparison, right? So, in particular, we'll be focusing on comparisons as the preference. So, it can choose a pair X and X prime. And what it gets back from this sort of labeling or indirect labeling comparison oracle is whether the value at X is bigger than the value at X prime of the labeling function. So you get Z, which is some measure of this difference, typically the sign of this difference of the labeling function. Right? And our goal is to minimize the number of labels needed using preference feedback in the form of comparisons to achieve a target error epsilon. So we'll be talking about what is the label complexity, how many labels do we need to get to accuracy epsilon, and then what's the comparison complexity, how many comparisons do we need? And we would want to compare these two and see how having access to comparisons reduces the label complexity. So we can broadly ask this question in a set of problems that people and including our own work has looked at. So I'm going to break it down into sort of two sets. So the first three bullets you see here are about optimization broadly. So convex optimization has been looked at by many people, where they looked at what if you only get to know the difference, right, or the sign of the function values at 2 points, right? And there are results about comparing it to the direct zeroth order oracle, which just gets the value of the function. We extended that work to also talk about non-convex settings, in particular Gaussian process-based optimization, and also reinforcement learning, specifically looking at policy optimization there. So I'll go a little bit more deeper into reinforcement learning today, but I'm happy to talk about any of these, during the Q&A session. And the next set of problems is more classical supervised sort of problems. So I've included classification and regression here, and also threshold bandits. So threshold bandits is a problem which is can be considered as a finite domain classification problem, where we have a bunch of arms and we have to decide which arms are above a threshold by pulling as few of the arms as possible. Okay, so every arm has a reward associated with it, and you want to figure out which set has a reward bigger than a threshold. So it's kind of like classification. We are trying to decide whether the probability of a particular label is more than half or less than half, let's say in binary classification. So the green works here are done by our group, and I'll be mentioning the references at the end of the talk. The blue one is work by others, and I have tried to put in the pointers here. So, the takeaway message of this talk is that in the first set of problems, which are all optimization based, comparisons alone suffice, and you get the rate of error decay, which is the same as for labels only. So, if you had the same number of comparisons as labels, right, you essentially get the same error rate. And this was shown for convex optimization, where it makes sense because a comparison is like the sign of gradient. So since gradient information suffices, the sign of the gradient can potentially also suffice, which some of these papers have made rigorous. Now, for non-convex optimization, you might think the same argument applies. It almost does, except that gradient is a local piece of information, whereas comparisons can be done between points that are further away, right? They don't have to be necessarily local. So, in some sense, they might be more powerful. But we show that in this case, also, you actually can see that comparisons carry the same value as labels. Okay, and the last piece I'll talk about is reinforcement learning, where again we have some preliminary results talking about how what the comparison complexity looks like, and it under similar conditions so far it looks similar as if you had the reward evaluations directly, and I'll talk about that a little bit more because there are some nuances there. The second set of problems is where comparisons alone do not suffice in the following sense, that I can have a comparison between two images and I can say which one is more likely to belong to one class, right? So that would be the comparison feedback. But that does not necessarily tell me where to put the threshold of calling it one class versus another, right? Similar issue arises in regression as well. So comparisons, what they can buy in that case is they can reduce the label complexity to depend on only one dimension. So no matter what your original dimension of the space is, if you have access to comparisons, it brings down your label complexity to one dimension. So an intuitive way to think about this is if I have comparisons between a bunch of data points that I want to classify or do regression on, then I can arrange them into a ranking, right? Comparisons can give you a ranking. And once you have a ranking or an ordering between all your data points, then it's just about finding where that threshold lies, right? So if you have essentially reduced the problem to one dimension, this ordering, right, that you have been able to obtain using comparisons, and that helps improve your label complexity to now just figuring out that threshold. And similar argument applies in regression as well, where the problem becomes that of monotonic regression in one dimension once you have the ranking. So that's the high level takeaway I want all of you to sort of have without going into any details. But once again, I'm happy to talk about details of any of these in the Q&A. So in the remaining time, I'm going to try to talk about reinforcement learning a little bit more. So once again, I think reinforcement learning is a scenario where preferences can really make a difference because rewards are extremely hard to design in the complex scenarios where reinforcement learning is used. It has been a big topic of debate recently that poor awards lead to unexpected and unsafe behaviors. There are several examples. On the right figure here, you actually see this was an example of a game where a boat that had to like complete a race and collect rewards on the way, or collect some, I guess, bonus on the way, ended up like scoring much more bonus points because it got stuck in a loop trying to collect a lot of bonus points, but never actually finished the race. Right. In this case, it happened because the reward was not necessarily poor. It was poor in the sense that the winning reward did not come until later. So there was a delay in when the reward is obtained. And hence, you see, again, behavior that was suboptimal. So preferences in this case can be easier because you can give feedback about, oh, this is not the right way to, for the agent to behave, and another behavior might be more suitable. This has been proposed and investigated empirically in a lot of works, but there's only about one piece of work which talked about looking at this problem in a theoretical foundational framework. So the paper by Novoselaar et al. Talked about asymptotic convergence of Thompson sampling under trajectory reward comparisons. And we'll instead be interested in finite sample because we again want to say how much does preference feedback help? Can we replace, because this is sort of an optimization problem where we're trying to find the right policy, then can we once again show that the number of comparisons can replace the number of rewards, right? And what does that comparison look like? So the setup is we have a Markov decision process. We work in the tabular RL sort of setting. So we have a certain number of finite states, actions, and a horizon. There's a deterministic unobserved reward. Deterministic is purely for simplicity. The reward is bounded between 0 and 1. We have a random state transition matrix. There's a potentially non-stationary policy pi that maps every state to an action. And there's a value function which specifies the expected reward of a particular policy, right? So that we assume that the value function also lies between 0 and 1, in addition to the reward lying in 0 to 1. So it's bounded. And our goal is to find a policy such that with high probability, the value of the policy is only epsilon suboptimal. Now, the first point I want to make is that there can be preferences between a lot of things in an RL problem. You can talk about preferences between actions, preferences between states. The framework we are working with and that past work has worked with is comparison between trajectories. So given two trajectories, you can get feedback about like which one is to be preferred over the other. And another thing we assume is that it is possible to compare partial trajectories. So you don't necessarily need to see the entire trajectory. We can also obtain comparisons on partial trajectories. So one interesting point that came up is that even with perfect preferences between trajectories, we might not recover the optimal policy, right? And that's essentially because, I'll give you a counterexample here, but it's essentially because comparisons between trajectories may not necessarily reflect the comparison between policies, because a trajectory is just a draw from a policy, right? So as a counterexample, we can see that pi has reward 1 with probability 0.4. Let's say we just have two actions, right? And 0 with probability 0.6. So it's in a particular state, and that's the setup. And pi prime always has reward 0.1. Then we see that a randomly drawn trajectory tau prime from pi prime beats a randomly drawn trajectory from pi with probability 0.6, right? Because it has a higher reward, 0.1 compared to 0. But if you look at the expected reward, then pi has a higher expected reward. So in general, we can actually show that there exists MDP with three policies such that they are intransitive, right? So pi 1 beats pi 2, beats pi 3, but then pi 3 beats pi 1. So this limits fundamentally the way preferences can be used. However, there's a not too unnatural assumption that can be made, which is that the comparisons are actually stochastic. And if we have two randomly drawn trajectories from two policies, then the probability that one trajectory beats another trajectory is related to the value of the difference in the values of the policies. Okay? So that's the assumption we'll work under. And the setup we have is we'll be talking about an algorithm that tries to reach a particular state. When it reaches a particular state, it does dynamic programming. So we'll be trying to reach a state at the last step, right? Finding a way to get there. And then at that state, do a dueling bandit, right? So basically, we have a bunch of action choices. We'll treat those as the arms in a bandit and use some off-the-shelf dueling bandit algorithms that have already been proposed in the literature to figure out the best action in that particular state, right? So the way the reachability is ensured, that we'll be reaching different states, is via a synthetic reward function that we define. And that function has also been used in previous work for different reasons, particularly to encourage reward free exploration. So here, the synthetic reward function is just again one if the algorithm reaches the state, and zero if it doesn't. So the idea is that we'll play these different reward functions, the synthetic rewards that we have for every state. We'll try to get a trajectory that hits that state, and once it hits it, we'll do a dueling bandit to figure out the right action. Then we go one step backwards, go to step h minus one, once again try to define a reward that's one for hitting a state at that step, and repeat this process. So it'll become clear once I put it up. So here we go from the last H is the capital H is the horizon. We go from the horizon backwards. For every state at that step, we define a reward, which is one if the state is reached, zero otherwise. And so, for example, here, right, the state S, and we run any value based, right? So now we have a reward function. It's a synthetic reward, but we have it so we can run any reward based tabular RL algorithm to optimize that reward. And whenever it hits that particular state, we play a dueling bandit algorithm, right? And we generate a trajectory using it, starting at state S, right? So once we have that, we have the best action at step H in that particular state, and then we backtrack. We go to we go to all the different states, and then we backtrack and go to the previous the state at step H minus one, and repeat this process until we have the entire trajectory all the way to the back, right? Step one. All right, so how does the sample complexity look like? Well, it depends on how we distribute the error over the states. I'm just going to present the simplest version, but I'm happy to talk about, again, more detailed version later on. But if we say that we spread the error uniformly over all the states, then, so essentially epsilon over h for every state, then we get a step complexity that's written over there. It's h cube s square a over epsilon cube plus some polynomial again in s, h, a, n over epsilon. And comparison complexity, which was our focus, is h square sa over epsilon square. So put it on some footing. We wanted to see, right, how this compares to if we had rewards only between the every step instead of having comparison between the trajectories. So we can compare it to a value-based RL algorithm, not one that's used on the synthetic reward we define, but that if we had the reward for every action we were taking, then that particular algorithm would take this many number of steps as written there, and these many episodes. So episodes, we believe, is the right thing to compare against comparison complexity, because when we are doing one comparison between two trajectories, that essentially gets us information equivalent to an entire episode, right? So instead of counting the reward at every step, the right way to compare is we look at how many episodes does a value-based, right, reward-based RL algorithm take, and how do the number of comparisons between trajectories compare to that. And we see that they exactly match up, right? And this holds for under the same assumptions on the reward and the value of the tabular RL setup. So we see that the comparisons match the number of episodes in reward-based RL, which is nice and in agreement with what we know for optimization in general based off of comparisons, that the comparison complexity is similar to the label complexity. And in fact, only comparisons suffice to do that optimization. So I'll conclude with some open questions. One is in terms of the comparison complexity bounds. So there has been recent work after, actually this was our paper in NeurIPS 2020, and after our paper, there came out a few papers which talked about getting the preference, the reward-based RL complexity independent of the horizon. And the open question is whether the same is true for preference-based RL. It's not completely clear because of the way we used the existing results. We require an instance optimal bound to get the preference based RL bounds, whereas the current improvements in reward based RL, showing that it's independent of horizon, is actually a worst case bound. It's not instance optimal. So it remains unclear whether this is true for preference based RL or also or not. Uh, Moreover, we have, as I said, another version of this algorithm where instead of distributing the error uniformly over all the states, we make it proportional to the reachability of a state. In that case, we actually get slightly improved step complexity, which is the runtime, right? But worse comparison complexity. So I think that the trade-off between step complexity and comparison complexity is also something that can be improved. More broadly speaking, I think a bunch of the algorithms we developed in this framework with dealing with preferences and labels, they some of them are adaptive, but some of them are not. So trying to come up with hybrid reward preference feedback, which take advantage of preference feedback when it is actually more accurate and less noisy than the direct reward based setting, right? But if it's worse, then automatically discards it, would be interesting. So hybrid reward and preference based frameworks, I think, are still open, though some of our algorithms do deal with it, but not fully. Another issue is limited rounds of interaction. How many preferences can we obtain, and how many times we can go back to a comparison oracle, which tends to be a human often, to get their feedback on the trajectories may be limited. So, taking that into account and developing adaptive algorithms that can adapt to right their budget according to how many rounds of interaction are allowed would also be interesting. Finally, other forms of feedback, right? So we have only looked at comparison between trajectories. We could talk about comparisons between actions and states, as I previously mentioned, but also comparison between features. Which features might be relevant to a task versus not? That's another form of feedback we can obtain and can help reduce the overall supervision that's needed. And more broadly, there are other forms of feedback like causal relations that might be known, right, and can serve as alternative forms of supervision, right, that we might want to include knowledge graphs, demos, instructions, and so on. And developing a foundational footing for any of these is completely open. All right, with that, I'll end here. Here are the references I had mentioned for our work that deals with looking at this sort of trade off between comparisons and labels. And most of these works are by my student Yi Chong Shu, who's since graduated, but just wanted to put that up, and some collaborators. Thank you so much.